causation in physics. So I've just written this big book. It's out in October, November. It's a fat book, 100,000 words. And that's a picture by my daughter who's a painter. Isn't it nice? Okay, and the book develops theory of causation, which I will tell you about some of. But what I want to focus on today is that a few places I get involved with issues in the philosophy of physics, not especially my area, so I'd like to tell you about that and ask for advice and guidance. Too late for the book, but it would be nice to know the truth. So that's where we're going. So first of all, that kind of three parts. First of all, I'll tell you about the theory of causation, give you some motivation for it. Then I'll talk about a bit about analogies I draw between causal asymmetry and thermodynamic asymmetry. And then I'll say some stuff about indeterminism and causation in the context of quantum mechanics. Okay, so here's the theory. A causes B if and only if it's an ancestor in a system of deterministic laws with exogenous independence. If I wouldn't put exogenous probabilistic in because it's quite important for my whole project to keep apart probabilistic dependence and independence from causal dependence and independence, because this is going to be some of the explaining of that probabilistic independence. I'm going to refer to those recursive structure deterministic laws with exogenous probabilistic independence as RLI, recursive laws independence. These aren't very different from things you might have met in philosophical work on causation, statistical work on causation, systems of structural equations. And here's an example that I'll use running through the talk. I suppose we have three quantities, a type of school. First instance, think of it as kind of the amount of money the school has available. Second quantity, the exam results. Exam results kids get in public exams if they've been at that school. And household income, the available money in the household they come from. And then I'm going to have three error terms, noise terms, the exogenous terms. And we might write down equations. I mean, educational sociologists will write down equations like this. They'll say household income is a function of various background factors. We don't quite know what they are, but let's assume that they're there and it's a function of them. And the affluence of the school is a function of the household background of the kids and a bunch of other influences. And the exam results are a function of household income, school wealth, and another bunch of background influences. Okay, so these are recursive. No term appears on the right-hand side until it's appeared on the left-hand side. That imposes an order on the variables. I've assumed linear equation just for purpose of illustration. You might think that's a bit silly in the case of schools. I mean, the schools really linear? Maybe they're just public and private schools. In fact, the story will generalize to pretty much any kind of functions. Not quite all the points I'm going to make today will generalize, but pretty much the central ones will. So, more generally, we have a set of macro quantities. We have a set of micro quantities, which are the kind of background terms. And then we have laws in order. First macro variable depends on its noise term. The second macro variable depends on the first macro variable and its noise term, and so on. And so we can represent the system of laws or equations by a directed acyclic graph like that. I talked about the background terms, the E terms being probabilistically independent. So I'm assuming, in addition to deterministic equations, a probability distribution over all the quantities. In fact, given that each quantity is a deterministic function of the noise terms ultimately. Probability distribution over the noise terms will impose a probability distribution over all the terms. Okay, that's, people haven't met it at all. I mean, some of you will be familiar, some of them not so familiar, but in fact, people who know contemporary metaphysical work on causation will have seen systems of equations like this under the heading of causal models, systems of structural equations. And philosophers of causation in the David Lewis tradition have started, I mean, they've got them from statisticians like Judea Pearl, but have started positing structural equations, sets of structural equations like this to help them understand counterfactuals and actual causation. And it's pretty trivial to get a nice theory of counterfactuals out of a system of structural equations like that. If you want to know what would have happened in a particular situation if S had a different value from its actual value, just toggle S to its actual value, hold fixed everything else that doesn't depend on S in the equations at their actual value. So you toggle S to its non-actual value, apply the equations and see whether the result changes. That will give you a so-called interventionist semantics for counterfactuals. Tricky cases of actual causation where a result doesn't counterfactually depend on something else, but actually cause them. Lewisian philosophers try and analyze those tricky cases using structural models as well. And I'm very happy to go along with all that. That's all fine by me. What I don't like about the mainstream use of structural models is it seems to me to be assuming what I really want to have explained when I do analysis of causation is where does the directionality come from? What justifies you writing arrows? You know, after all, we've got equations and we can rearrange the equations and we'll still have the same set of equations, the same joint constraints on the values of the variables involved. Why write them one way rather than another? Remember, David Lewis came into this causation business saying he didn't like regularity theories because they couldn't deal with the direction of causation. Hence his counterfactual theory is going to solve that problem. And now it turns out that most of the people working in this tradition just help themselves to a solution to that problem. Anyway, my suggestion is we can solve this problem. We can tell you why you have to write the structural equations with one set of dependencies rather than another by imposing the requirement of probabilistic independence. So we could arrange the equations I had at the start, just switch the first two around, make S the first macro quantity, H a function of it. And I mean, it's quite simple to transform the linear equation I had at the start. But if you do that, these two terms will cease to be independent. So you can see here, this is a linear function of H and S, and this is ES. And they're not going to be probabilistically independent. It's pretty obvious that any reordering of a set of linear equations will destroy the probabilistic independence if you start with the exogenous terms being probabilistically independent. No reordering with respect to that. So I say structural equations will capture causal order if and only if the exogenous terms are probabilistically independent. Now, in fact, you might start worrying about counterexamples in both directions, and I look at that a lot. Cool. But let's run with that for the time being. Motivation. Why believe this story? I've just pulled it out of thin air. It actually has some support from intuition. The basic idea is that if you have a cause-effect pair, the effect will have independent sources of variation. I'll come back to it in a little while. Everything that varies with the cause, the effect will vary with those things too, but some things vary with the effect, won't vary with the cause. Effects have something independent of the other causes. So think of it. Smoking will vary with social class and parental smoking and I don't know, yellow fingers, and you'll find that all those things cancer varies with too. You'll get more cancer among non-social class parental smokers, people with yellow fingers. But cancer will vary with some things. Think of radon gas exposure, causal bladder cancer. There's no reason to suppose that will vary with smoking, that you'll find more radon gas exposure among smokers. So it's kind of intuitive that effects have independent sources of variation. But in the book, I don't make very much of that. My main motivation for this theory is it explains something which to me has always cried out for explanation, and I find it shocking that so much of the literature on causation, including all the interventionist literature, just doesn't address this question. So I think we need the theory I've given you to explain why causal inference works. So causal inference is a business that goes on outside philosophy, in fact, outside academia. I mean, it goes on, well, it goes on medical epidemiology and educational sociology and all kinds of sociology and economics and marketing. People are trying to figure out what's the causal structure among various quantities on the basis of their probabilistic relationships. So just to illustrate the idea, suppose the education sociologists discover that school time is correlated with exam results. More fancy schools get better exam results. And household incomes are correlated with fancy schools, correlating with exam results as well. But this correlation disappears when you hold H fixed among kids from the same level of household income. The fancy school doesn't produce any better exam results. The truth is not very far from that. In fact, schools make surprisingly little difference to kids' performance in academic tests. But let's suppose it for the sake of the argument. The natural conclusion would be that H is causing both school time and exam results on the basis just of these probabilities. In fact, that's not the only possibility. If you had, or I could E this, if you had either of these causal structures, you get the same probability distribution, the same correlations. I mean, of course, we know that, sorry, I got this wrong, school time is not going to cause household income because the time is wrong. But one interesting thing about causal inference is that, in principle, it doesn't need to assume any time ordering. You can just give it all the variables, not worry about their time ordering, and it will tell you which is causing which. In fact, well, immediately tell you which is causing which, because so far I've got a bunch of correlations that don't tell you which of these three is the right one. But if you had another quantity over here, I don't know, school endowment that wasn't correlated with household income, another quantity over here that was correlated with exam results but not household income. If you had two colliders like that, then that would force this causal structure. Because if you had either of those, you wouldn't have the independencies that you observe here. So, while a lot of the literature, people like Jim Woodward and Chris Hitchcock are very skeptical about the ability of probability distributions alone to determine causal structures. The truth is, so I'm jumping ahead of myself. And go back. I want to say this first. The truth is that given enough correlations among a set of quantities, the principles behind causal inference, which I'm about to give you there on the previous slide, suffice to fix a unique causal order over the set of quantities. You need enough. Remember, I just gave them 3 variables in there. It wasn't enough, but I brought in 2 more, and that fixed the problem. Now, inferences like this do need to assume causal sufficiency. They need to assume that your set of quantities, for any pair that have a common cause, your set includes a common cause of them. I made it rather complicated because there's a lot of common causes once you have one common cause, but you have a common cause for every pair of quantities in the set that has a common cause. And if that's not true, then these inference principles will lead you astray. I mean, think of this one here. I said, let's suppose there's something here that's uncorrelated with that. If in fact that was the product of a hidden common cause, you'd have the same probability distribution, but it wouldn't be true that this was the cause of that. So you have to assume causal sufficiency. The other two principles behind causal inferences, I'll put them here because I'll be referring to them. Again, there's two bridge principles, and one takes you from correlations to causal structure. The other takes you from the absence of correlations to the absence of causal structure. When I say causal structure, I'm talking about, in here, I talk about causal links. Two variables are causal linked if one is causing another, or they have a common cause, but they're not linked if they have a common effect. The first principle, Reichenbach's principle, says if two variables are correlated, they must be causally linked. Either one's causing the other, or they have a common cause. And then, that in fact, the first part is a special case of a more general claim. If two variables are correlated, after you control for some other variables, they must be linked by some chains that don't involve those other variables. All those other variables contain a common effect. That's to do with correlations induced by controlling for colliders, but we won't talk about that until discussion. And the faithful condition is kind of the converse. If you have two variables that aren't correlated, then they aren't causally linked. If you have two variables that aren't correlated after you control for some further variables, then they aren't causally linked by anything that doesn't go through them. So there's two principles to infer causal links from correlations and infer the absence of causal links. The absence of correlations. And that's enough to determine the causal order given a rich enough set of correlations. Now, I say you need causal sufficiency. And of course, in practice, that's a big danger. That's an ever-present danger. That's what makes a lot of people worry about these kind of techniques. And I think that you never can really be sure until you've done a randomized trial, or you need something approximating to a randomized trial. You need instrumental variables. I'm quite keen on the idea that in some cases you can just look at some correlations and be sure what's causing what. Think about how we discovered about smoking and cancer. But I don't want to worry about those methodological issues. I'm interested in this prior theoretical question. What is it that makes these causal inference principles work? What in the nature of causation allows us to infer causal structures from correlations? And it's kind of strange that none of the philosophical theories of causation so much as address this question. Counterfactual theories, regularity theories, process theories, they don't even talk about this question, let alone give an answer. There's a little tradition in philosophy of science that does give an answer, and that's probabilistic theories of causation, which in effect try to reduce causal structure directly to the correlational structure. So you get Good, Xerxes, Wesley Salmon, at times before he became a process theorist, Mark theorist, and Wolfgang Sperm is rather keen on this idea. And in fact, you can kind of give a explicit definition of causation in terms of correlations if you assume the bridge principles, and make an extra assumption that every effect has an extra source of variation. Dan Houseman points out, he doesn't believe this, that you can just give this explicit definition. A causes B, if and only if A is correlated with B, and everything correlated with A is correlated with B, and something correlated with B is not correlated with A. That's a consequence of the bridge principles and an assumption about enough available variation. I don't want to go this way. I think this is too quick. And the reason is that the bridge principles aren't, in fact, generally true. People point out there's lots of counterexamples to Reichenbach's principle. There's counterexamples to the faithfulness condition. We can't say something causes something else if and only if it's correlated with it and something else, because the first bit breaks down in both directions. This is pretty well known, that counterexamples to Reichenbach's principle, correlations that don't indicate causal links. Maybe it's sober, bread prices in London, water levels in Venice, go up and down together. No causal link. EPR correlations, I'm coming to that. Glider bias correlations, we can talk about that in the discussion. But these are all real correlations where there's no causal link.
Where there's no what?
Causal link.
Oh, causal link, sorry.
And here's those famous example of the failure of faithfulness, and multiply it. Birth control pills, pregnancy, thromboses. Birth control pills, as is well known, conduce to blood clots. So does pregnancy, producing blood clots, but birth control pills prevent pregnancies. And if the numbers just balanced exactly, you'd have no correlation between this and that, even though it's certainly causally linked. I mean, if all you cared about was not getting blood clots, wouldn't make any difference whether or not you took birth control pills, if Hesler was right. I mean, of course, that's not what we care about. So, I mean, this shows that there must be something beyond the bridge principles. These two aren't correlated. They're both correlated with this. If you apply the bridge principles, you're forced to think that these are caused like that. And that would be wrong. So I think we need to go deeper, and we need to go deeper and look at the RLIs, recursive structures of laws, the deterministic structural equations. What's going wrong with the causal inference practice is that we're dealing just with macroscopic variables, and we're just looking at probabilistic relationships. And we're kind of leaving out the microscopic details that are actually determining things. And because of that, we can get failures of faithfulness. We can get correlations that aren't the right kind of correlations. And what we want to do is think about the probability distributions as being generated by sets of structural equations, RLIs, with exogenous independence. And once you do that, then you can explain Reichenbach's principle. You can explain why any two quantities that correlated must be either one causing another or have a causal link. I mean, now I'm identifying causal structure with structure in ancestry in an RLI. So you've got two variables. In an RLI, each variable descends from some set of exogenous terms. If the two variables descend from disjoint sets of exogenous terms, then they're going to be probabilistically independent because exogenous terms are independent. So if they're correlated, they can't descend from disjoint sets of exogenous terms. They must have some kind of common ancestor, either a common cause or one's causing the other. So, and you can do the same conditioning on various variables, so you get a derivation on Reichenbach's principle from the assumption that causation is what I say it is. And that seems to be a very strong reason for accepting that account of causation. As for faithfulness, well, you can see now why faithfulness doesn't always hold. If you have two variables that are linked in a recursive structure, well, in a normal course of events, you'd expect that to produce a correlation. but in some cases there'll be a kind of lucky happenstantial play out, and then you'll get a faithfulness failure. So now everything falls into place. If you think causation is RLI structure, you can explain Reichenbach's principle. You can explain what's wrong with the bad correlations. They're correlations that you shouldn't be trying to infer an RLI from, the structure of an RLI, because they don't come from an RLI. Well, I mean, that would take some showing, and I'll do it in the case of the EPR correlations. But these time series correlations, they aren't being generated in the way an RLI is generated. We can talk about that more. So you can do these causal inferences, provided you've got probability distributions which are reflecting an underlying RLI. And on that assumption, you can infer the structure of the RLI from the correlations. In fact, it's pretty freaky. You've got this RLI with all these dependencies, and the dependencies might have any form and there might be any parameters, but you don't need any of that to be able to infer just from dependencies and independencies what's ancestral to what in the RLI. It's a very powerful non-parametric form of inference. Okay, so that's good. Everything falls into place, and in particular, we can now make honest people of the Lewisians who are appealing to structural equations to explain counterfactuals and actual causation. Okay, not too bad. Now for some physics. So this is what happens in chapter 5 of the book. I address the challenge. Look, it's all very well, but this sounds pretty pie in the sky. There's causation going on all over the place. And I say in every case of causation, there's a set of equations of a specific kind underlying the causal relationship. Why should anybody believe that? And the answer I give is, well, let's draw an analogy with entropy increase. And there's entropy increase going all over the place. And why is that so? And I say that's because there's sets of dynamic equations with probabilistically independent initial conditions. And a lot of people think that's the right answer. And if you're happy about that for entropy increase, why shouldn't you be happy about it for causation? Some philosophers who know the recent literature on thermodynamic asymmetries might find this a bit odd, because some of that, much of it, contrasts explanations of temporal asymmetries that are causal from ones that are thermodynamic. Particularly Matthias Frisch, who talks about an asymmetry which is quite close to the material I'm working with, the asymmetry of records. He says we should explain that in terms of causal principles, in particular the principle of the common cause, and not in terms of thermodynamics. He looks at Albert and Lowe's somewhat hand-wavy account of the asymmetry of records. He says that's not a good way to explain the asymmetry of records. Here we can explain it in terms of the common cause principle, two things. And the common cause, then their effects will tend to cluster, and that's the explanation of records. But in fact, this, to my mind, this contrast of causal explanations of temporal asymmetry with thermodynamic ones is misleading. What we've got is a contrast between Albert and Lower style explanations of temporal asymmetries and the right kind. I'm with Frisch about the right way to explain the asymmetry of records, and Athermostratus has a nice paper in Synthesa filling out this line of argument. But I don't think of this as a way of explaining the asymmetry of records, not in terms of statistical mechanics, but just a special case of such an explanation. And so I want to appeal, rather than to Albert and Lowe, to David Lewis, David Wallace's recent work on thermodynamic asymmetry. And Wallace criticizes Albert and Lowe for not giving us any understanding of quantitative understanding of approaches to equilibrium by non-equilibrium systems. Now, I mean, is this a fair criticism of algorithm? No, I mean, they don't set themselves out to be doing it. Everybody says, okay, here's all this interesting explanation of entropy increase that you're not touching on. I think they say, well, we never promised to do that. But from my point of view, it's just the kind of thing that I want to appeal to in drawing analogies with causation. So, Wallace talks about, we take some macrostate, some time, we partition all the microstates, we assume all the microstates in a certain cell have equal probabilities. This results in using correlations between some of the elements of the microstates. And then you apply dynamics to this coarse grain partition, hold it for a while, stop, coarse grain again, and so on. And that's Wallace's account of what goes on in Boltzmann-Yates theorem, in BPGKY hierarchy. He also talks about various treatments of Brownian motion have the same form. And I want to say that systems of structural equations, my systems of structural equations, are very similar in terms of the kind of asymmetry we have. Here we have a system of equations, allows us to predict school time in terms of home income, on the basis that these terms are independent. If we invert the equations, still perfectly good equations, these terms aren't independent, and now we can't anymore do forwards predictions. So in both cases, I want to say the statistical independence, the asymmetry is constituted by the probabilistic independence of initial conditions as opposed to the final conditions. That's what goes on in causation, and it looks just like what goes on in the H theorem and similar statistical mechanical treatments. Let me just give you a bit more on how the independence assumptions I've got allows predictions in one direction and not the other. So I'm going to predict school type on the basis of home income. And we got, what was it, S equals A times H. So here's the line. And I can do this because the noise around this point is the same wherever we are on H. That's to say that the noise term for S, ES, is independent of H. H was just EH. If you invert the equations, then you can't do that. This term here isn't any more independent of that. And so you can't assume, when I'm doing it the other way around, going here, I'm down to here, you can't assume that the error terms here will be the same all the way along. And so you can't infer an expected value of H from a given value of S. Here's another example of the same thing. Suppose we add this equation to the first. So we've got school as a function of home income, and now I say their results as a function of home income. Schools have no effect on exam results. Well, that's a standard common core setup, and it'll predict. It's pretty trivial, given that the error terms are independent, that school exam results will be correlated, but the correlation will disappear when you hold home income fixed. If you try and do all that backwards, it just doesn't work at all. You could add, okay, I had this bad equation that home income was a function of school. You could add to that exam results were a function of school. If the error terms were independent, this would imply that there was an HE correlation that was screened off by S, but because we've got things jumbled up and the error terms are independent, that prediction would be false. It wouldn't be borne out empirically. And that looks just like the same as you get in statistical mechanics. So when we do the H theorem, we focus on the velocity of particles before they collide, and we assume that that's independent. And then the H theorem shows us that entropy will increase. But suppose you do it backwards. You consider the velocities of pairs of particles after they collide. You could assume that they were independent. And if you did, then you could run the analysis backwards and show that entropy must have been decreasing as you went forward. And that would be wrong, because it would be empirically false that the earlier state of the system was lower entropy, higher entropy in the later state. So the analogy looks very close. And I want to say, okay, is it exactly the same thing? Or are they analogous? Interesting question. Some interesting arguments you can give if they're exactly the same thing. Let's leave that for later. Let me just finish this bit with a concession or admission that, as Hugh Price is very keen to stress, both these stories explain one temporal asymmetry by assuming another one. We're assuming that the initial conditions are independent. And you might think that, assuming independence, can't you just do that in the absence of any other considerations? And maybe this context and makes sense. Okay, but not in this context where we're thinking about temporal asymmetries, as Hugh Price is very keen to point out. If you look backwards down the other direction of time, initial conditions are not at all independent, precisely designed to shoot the pedal back up. So I'm just assuming a certain temporal asymmetry to explain both causal and thermodynamic asymmetry, but that's fine by me. Maybe that further temporal asymmetry hands out for further explanation, and I'd be very glad to hear what it is, but my aim is just to show that there's a close analogy between causation and thermodynamics in support of my account. Okay, finally, indeterminism. So quantum mechanics implies indeterminism-ish. GRW implies indeterminism. Everett implies indeterminism with respect to the branch that we're going to go down, that my successors are going to go down, but down any branches. Determinism, but the indeterminism is just episteme. But for the moment, let's just take the indeterminism at face value and see what happens to my analysis. And what's very striking is that the derivation of Reichenbach's principle from the idea that events are governed by structures of ROIs falls apart once we allow indeterminism. And basically, Reichenbach's principle was defended by showing that the values of these macroscopic quantities are determined by certain antecedents, microscopic quantities, and if they're independent, then these are determined to be independent too, because they're determined. But if we switch from structural equations where the dependent variables are determined by the earlier ones to ones where the chance of the dependent variables is determined, then this argument isn't tight anymore. You might have that the chances of these two things are determined by probabilistically independent things, but that leaves room for them to coordinate their actual values within the space allowed by there being chance here. Sorry for being late. That's fine. And of course, that's exactly what happens in the EPR correlations. You have source to measurements of quantities, the chance of the measurement is determined by state of the source and choice of measurement and perhaps various bits of measurement noise. But even after all that's fixed, what you're getting determined is the chances, and then the results coordinate themselves within the space allowed by that. So in a chancy quantum world, we shouldn't believe Reichenbach's principle. It's not generally going to be true. It's not generally true. Linear period correlated events, either one's causing the other, or they have a common cause that screens off their correlation. That's just not okay. Well, all right, okay. I'm assuming, and we'll come back to this, that one's not causing the other because they're space-like separated, and whatever we call the chance, it's not a chance that screens off. Yeah. So whatever we call the source, it's not a source that screens off their correlation. So the question is, why does the fact the world is a quantum mechanical world not undermine causal inference? And I think the right answer is, okay, sure. I mean, there are real EPR correlations in the world, but I don't know if I should be saying that they're rare or that we really don't see them very much. We don't notice them because they require very carefully engineered experimental setups.
You should say the second thing, yes.
Yeah, well, we don't notice them very much. They're there all the time, okay. But I think a bit more. I mean, are they there involving macroscopic quantities all the time? Okay. Anyway, we don't see them. We don't see them. We can come back and talk about exactly why we don't see them. What we do see is the result of the correlation between their chances. We had perfectly good deterministic equations fixing the chances of, say, two separated macroscopic quantities in some cases, and we will observe correlations display this correlation of their chances. But you won't just observe any more correlations than that, because the macroscopic events that we're observing aren't precisely selected to display extra correlations. So, perhaps we shouldn't take it that all macro events are governed by pseudo-deterministic systems of laws. Perhaps all the macro events that we attend to, come back to that. But the point is that in the actual world, it seems pseudo-deterministic. In this sense, okay, in the Bayesian network causal inference literature, there's a notion of pseudo-indeterminism, which is when you just look at macroscopic quantities, ignore all the macroscopic quantities that perhaps are determining them. People like Dean will say we've got pseudo-indeterminism, really at the bottom, my ROI, everything's determined. It just appears indeterminate because we like looking at all the details. I've got a converse notion, pseudo-determinism, even though it's really at bottom indeterministic. Systems of law-like dependencies display their structure in correlations in just the way they would if they were deterministic. So I'm happy to assert that A causes B if and only if it's an ancestor of the recursive structure of deterministic, the pseudo-deterministic laws in the exponential single dependence. And then everything can proceed as before. In the book, I spent quite a lot of time on candidate analysis of counterfactuals and actual causation. Proceed as before. Can the connection between causation and action proceed as before? The connection between causation and action, I take rational actions to be ones that there's a certain probability of counterfactual dependence between the action and desired results. One time book showing that the standard measures of effectiveness in probability distributions measure the probability of counterfactual dependence. And I have to work quite hard to show that that also stands up even after we move to pseudo-determinism. But I won't talk about that now. I'll quickly finish by saying a couple of things about the EPR setups themselves and what should we say about them causally. After all, they are some real ones, and they involve macroscopic quantities in the causally interacting world. What are we supposed to say about the structures we have there? I have a little short section in the book about this because I say I've got nothing special to contribute here, but I'll say something for the sake of completeness. And what I say is this quantum causal modeling, which seems to me kind of interesting if you understand it. It's using observed correlations and an assumption of probabilistic independent background terms, but not determinism or pseudo-determinism. And they're trying to figure out how you can figure out the structure of laws from the observed correlations given the assumption of independent background terms. All seems good to me. I'm not sure how philosophically satisfying that is because we're still left with all the standard questions about how to understand quantum mechanics. I mean, it doesn't give you an answer to the measurement problem. And in particular, it doesn't give you an answer to how it is that results are coordinated across space in the EPR cases. I mean, that's still a puzzle, it seems to me. How good you are at inferring the dynamic structure from correlations. And why is the EPR a puzzle? Because these results are coordinated. They aren't coordinated by the straight of the source because that leaves different results open on both sides, and they can't be coordinated by each other because they're space-like separated. And so that's an issue that still needs addressing. I think that both GRW and Bohm posit what come out to be superluminal causal influences in the sense of my theory. I applied my theory to what's going on in EPR setups. As they see it, we're going to get causal connections, space intervals. Something on this interesting work, good work, Wood and Specken's well-known paper that look at Bohm and GRW and say, well, we've got these causal structures. We know quite a lot about causal structures from the causal inference literature. These causal structures are going to involve faithfulness failures. There'll be fine-tuning, cancelling out of parameters so that we don't observe a correlation when there's a causal connection. And I think that's true. But I don't see it as a kind of extra big problem for Bohm and GRW. Wouldn't Specker seem to suggest that we have to believe in faithfulness because causal inference is a good thing, so these people deny faithfulness, that's bad for them. Doesn't seem to me it's any extra bad for them than we could have seen there was something odd about their theory before we started thinking about causal inference. It's obvious from the start that you can't convey information from data there by wiggling something, and that's an thing due to faithfulness failures. So I take this puzzle, what explains the coordination across space-like intervals, to be a good argument for Everettianism, because that gives us an account of the correlations without positing superluminal causal inference. And Am I going to do this? Right, I mean, forever I mean, you get both results on both wings. There's no coordination. There's only coordination when you get to the forward light cone of both wings, and then you will get worlds where you see all combinations in proportion to their quantum mechanical probabilities of those combinations. There won't be any worlds in which quantum mechanics rules out certain combinations, and that's the whole explanation of the EPR correlations, and no similar anything going on there. So it's interesting that some of the quantum causal modeling people end up with the same conclusion in a way, that only causation in the EPR setups is the source causes the spatially extended entangled future system, and there's nothing more to say about the causal structure. So anyway, I will stop at that point in time. Thank you.